Hello, this is David Carnell. I'm presenting this webinar on Tribological Design Guide for Rolling Bearings on behalf of the Tribology Group of the Institution of Mechanical Engineers. We're going to talk about the different types and their load and life capabilities. So some fundamental definitions. What is a bearing? A bearing is a device supporting two bodies in relative rotary motion under load. A rolling element bearing has rolling elements of spherical or basically cylindrical form in an ordered set between two conforming raceways supported by hydrodynamic or boundary lubrication. We have to have lubrication for the reason that if you stand on a railway platform, you may notice that the track and the wheels become polished. This is because as the rolling element, in that case the wheel, passes through the loaded zone, it flattens a little bit and the track dips a little bit. And the wheel has to solve this by slipping at the front and back of the contact zone. On the railway, it causes polishing. We cannot afford that in a rolling bearing, so we have to have lubrication, keeping them apart, but only just. Then moving on to types of bearing, a radial or journal bearing supports radial loads and defines mutual location perpendicular to an axis of rotation between two bodies. A thrust bearing, on the other hand, supports axial loads and defines mutual location parallel to an axis of rotation between two bodies. A radial and thrust or combination bearing combines the properties of radial and thrust bearings in a single unit. And sometimes a predominantly radial bearing will have a location bearing. That's a secondary bearing that provides mutual location of the bearing bodies in the plane perpendicular to the primary motion. And this may well be integrated into the primary bearing. So I'm going to talk about rolling bearings, the basic types, their strengths and limitations, the primary determinants of life expectancy, calculations of fatigue life capability, dynamic and static load ratings, limiting speed, the concept of thermal speed rating, and installation and internal clearance issues. I shall give some formulae and examples to aid understanding of bearing behaviour, but please note that manufacture of rolling bearings requires specialised equipment and knowledge, and real-life applications may well need additional factors from BS ISO standards and manufacturers' catalogues, and they will be referenced during the slides. So here is a chart of basic types of rolling bearings. I'm afraid it's a little bit difficult to read because there's a lot of information in it, but you can see that there is a comparison of the radial, axial load capacities, the speed capability, and how much misalignment each type of bearing will accept, and there are diagrams on the right to illustrate each description. I won't dwell on those, you can go back to those at a later stage. Primary determinants of rolling bearing life. The classic determinant of rolling bearing life is the Hertzian stress. This was worked out by Hertz, who calculated correctly that the maximum shear stress in a rolling contact is not on the surface, but below the surface. It explains why fatigue cracks suddenly appear at the surface and a lump of material pops out. You can see this on the highway anytime, where a pothole will appear overnight, and this is the same effect on a larger scale. So fatigue cracks start below the surface in this area of maximum stress. They tend to be triggered by discontinuities in the crystal matrix of the steel. So to make rolling bearings really successful, we use ultra-clean steels, and there is an ISO 683-17 which defines the composition of this type of steel. We have to avoid too much oxygen content because that promotes oxide inclusions, and inclusions and hydrogen embrittlement weaken the crystal lattice. Plastic deformation appears around the oxide inclusions, the crack propagates to the surface and releases a spall, as I've already mentioned. So failure of a bearing in this sense is the cumulative result of stress repetitions on these randomly located flaws. There is, however, another mode of failure that becomes increasingly common, and this is surface distress. If the lubricant is degraded, or simply not viscous enough, then there's a loss of the contact film, and surface-initiated failure will take place before the Hertzian failure occurs. So it's important to be clear about which kind of failure may operate in any particular application. So staying with the Hertzian concept, let's calculate the fatigue life capability of a bearing. We do this by defining a dynamic load rating. It contains factors for the physical bearing parameters. That's the rolling elements, their size, what sort they are, the pitch diameter, some factors for material, and some factors for manufacturing excellence. Not every bearing manufacturer is able to achieve the highest standards that are available in the market. There are then factors for operating environment, for load and speed regimes, mounting factors, lubrication, as you would expect, environment, contamination, and the reliability required. And the complete theory can be found in BS ISO 281, and there's also a supplementary technical report, ISO TR 1281-1, where you can find the complete latest form of these theories. For ball bearings, it works out that this dynamic load rating is related to life by a cubic law. So the load rating divided by the load raised to the power of 3 is proportional to the life we can expect. In the case of roller bearings, it's slightly different. The power is 10 over 3, but the relationship is pretty much the same. So here is more detail on the radial ball bearing capacity factors. The basic dynamic load rating, we use the symbol C suffix R to indicate that it's radial. We have a factor, BM, for material and manufacture, which also varies with the detailed type and its construction. FC is a geometry and material factor. Z is the number of balls. Capital D suffix W is the ball diameter. And I cos alpha is the number of rows I multiplied by the contact angle factor related to the contact angle in the bearing, which can vary between 0 and about 40 degrees. An increase in diameter has more effect than an increase in the number of rolling elements. So ball bearing rating life, for ball bearings, the L10 life is the basic dynamic load rating, CR, divided by the equivalent radial load raised to the power 3. And we define L10 as a fatigue life in million revolutions when 90% of a sample of bearings identically loaded at identical speed in well lubricated clean conditions, 90% of them will survive for that length of time. Now that introduces another important fact about rolling bearings. We can only define their expected life in statistical terms. We can pick up any individual bearing and say it will survive according to this formula, but we cannot be exact about when that particular individual will in effect die, just like people really. So now I mentioned already we need to consider what reliability we require, because 90% survival may not be acceptable in your critical application. So we now introduce some modifying factors. These might be greater or less than 1, although usually they are less than 1. And A1, you can see here about the reliability, says if I take a 90% survival rate as 1, if I want 99%, it's 0.25. So that means I need a nominal theoretical life 4 times what I would need for the regular L10 calculation. So this is quite an important factor. However, if you design for very high notional Hertzian fatigue failures, other modes of failure might actually dominate. If the lubricant becomes degraded, then the surface initiated fatigue that I already mentioned can occur. Contamination does the same thing. There is a thing called a fatigue load limit we'll come to in a moment, and rising vibration levels can also mess up the lubrication. Seal specification capability is important. If the bearing is in an aggressive external environment or there's high shock, then there may further be reductions of expected life. So we have a thing called AISO, which is a modification factor based on these real-life situations, and this is too long to put in this lecture, but you can again find it in ISO 281 and TR 1281-2 for the complete theory and the factors that may be appropriate in your application. So you may have noticed there was a thing called PR, the equivalent radial load. We need this little mathematical device to deal with a situation where the load may not be pure radial, but a combination of radial and axial loads. And the effect of axial loads on the effective radial load differs for various forms of ball and roller bearings. So we have these two factors, X and Y, which vary with the bearing type and design details, and again, if you go to BS ISO 281, you can find those in detail for real calculations. We then have the static load rating. When the bearing is not rotating, different criteria apply. The basic static load rating is based on a maximum permitted contact stress of about 4,000 megapascals, which is equivalent to a permanent deformation of the rolling element diameter of about 1/10,000th of the diameter. Even to achieve that, the bearing must be properly supported. So we have a capacity C0R, which has a factor F0, which is used to proportion the static load rating in a similar way to the dynamic capacity. And then the other factors, the number of rows I, the rolling element diameter dW, and the contact angle alpha are just the same as for dynamic capacity. However, low speed, high load conditions need extra care because there may be other limiting parameters. For example, in a ball bearing with its toroidal raceways, if the axial load exceeds the raceway boundaries, the theory breaks down. Or in a roller bearing, if it exceeds the rib roller sliding capability, which of course is not a rolling contact at all, then that may also be the limiting factor. If the axial load is too high in relation to the radial load in some kinds of ball bearing, then the contact situation becomes unacceptable and the theory breaks down. If the ring deforms, leading to creep during the mounting, then that can upset the internal clearance of the bearing. And of course, if the lubricant film is penetrated and effectively eliminated during a high static load situation, that may trigger surface initiated failure. Again, if you go to BS ISO 76, you can find the complete theory and the factors listed. So continuing, roller bearings fatigue life. As we already noted, this is a slightly different power rate relationship, but we also have some different powers for the number and size of rolling elements and the contact angle, which applies in the case of a tapered roller bearing. So again, we have a BM factor and an FC factor for material and construction, and I cos alpha is number of rows and the contact angle cosine raised to the power of 7/9. In this case, the number of rolling elements is to the power 3/4 and the diameter to the power 29/27. So in this case, the effect of increasing roller diameter is not so great as the effect of increasing a ball diameter in a bearing. We then have a basic static radial load rating, similar to the one for a ball bearing, and you can see that equation there, where LWE is the roller length for load rating calculations. That's not the nominal length of a roller you might measure with a ruler, but it's the length of the roller which is effectively in contact. We always profile the end of the roller contact zone in order to avoid edge loading stress raisers. So the effective roller length is something that bearing manufacturers have to know, and if you really want to know what it is, you may have to talk to them. And then there are dynamic and static equivalent load factors to apply, just like for a ball bearing. Fatigue load limit. Even with all those calculations, we still have to be concerned about the absolute effect of load on the contact patches. So we have to consider a fatigue load limit. Now this is important if you're considering some very high steady loads or external shock loads, or the same thing said another way, the maximum torque in a transmission, or sudden loss and restoration of drive, for example if you're driving over very broken ground. So we have a concept which has been established by research that for ball bearings this limit is roughly the static radial load capacity divided by 22, and there's a similar factor for roller bearings where it's radial load capacity, static radial load capacity that is, divided by 8.2. And you can see there are some additional notes there if you want to pursue this in more detail. Thrust bearings we define, and this is a bit arbitrary, as having a contact angle greater than 45 degrees. In this case, of course, we have a basic dynamic axial load rating, and for ball bearings, it's the equation we can see here, where again we have a material factor, a geometry, material and precision factor, and factors for the number of rolling elements and the rolling element diameter, which is exactly the same as in the radial case. However, this equation is only really correct if the ball diameter is less than 25.4 millimeters, or in old speak 1 inch. For roller bearings, similar sort of thing, but we have to have two equations here. The first one, C suffix A, has all the same constituents, but it's only correct when the contact angle is 90 degrees. That's to say there is no radial load capability whatsoever. And the second one, the modified CA, has a factor tan alpha in the middle of it when the contact angle is between 45 and 90 degrees. Again, dynamic and static equivalent axial load factors have to be applied, and if you have multiple row bearings, then more special factors are required. Again, these can be found in detail in BS ISO 281, and I don't have time to go into those in this lecture. Thrust bearing will of course have static load ratings. The basic static load rating for ball bearings is C suffix 0A, with an F0 factor from, again, tables in BS ISO 76. Number of rolling elements, the rolling element diameter to the power of 2 multiplied by the sine of the contact angle. You'll note there that I've written that Z is the number of balls carrying load in one direction. There are a number of designs of thrust bearing where there are 2 rows, but of course in the case of a thrust bearing only 1 row is active at any one time, and their capacities therefore have to be calculated separately. In the case of roller bearings, the equation is a bit different, as you can see there, and has a single modifying factor of 220 at the front, and the rest of it is about the geometry of the bearing, including the diameter of the rolling element, the contact angle, the number of rolling elements, the effective length of the rollers, of course, and the operating diameter again. And again, if you have a multiple row bearing, special factors are required, and you need to go to BS ISO 76 to find those. So, limiting speed. As you might expect, rolling bearings cannot run infinitely quickly, but at the same time some speed is helpful because that helps to generate a hydrodynamic film between the rolling elements and their raceways. There is a sort of semi-non-dimensional measure that we use for this. We take the bearing bore diameter and the outside diameter and divide them by 2 to arrive at the mean. That approximates to the pitch circle diameter in most bearings. We measure that in millimeters and multiply it by the speed in revs per minute. And this gives us this semi-non-dimensional factor where if I'm making a regular ball or roller bearing, cylindrical roller bearing that is, not tapers, then they can't go quite so fast, or sphericals. Of normal catalogue precision with grease lubrication, this limiting DN factor is around about 500,000 millimeters times revs per minute. If I'm using oil bath lubrication instead, the limiting speed goes up to 650,000 millimeters times revs per minute. It is possible to run much faster than that with higher precision, or if you prefer it the other way round, closer approach to perfection with special constructions, and the shaft and housing have also to be of higher precision if this is to work. Normally oil mist or oil jet lubrication is used, typically in machine tools, because that avoids creating unwanted friction losses. You can go even faster with special raceways, ceramic rolling elements. Silicon nitride is less dense than steel, so the centrifugal force inside the rolling element itself is less than it would be with a steel one. As an aside, somebody once proposed making hollow steel balls to deal with this problem, but nobody could ever get the hole in the middle. So now we have the ceramic ones, which are very successful. But again, the whole installation has to be of great precision for success. Ultimate limiting speeds in these conditions can be between 2 and 4 million millimeter rev per minute, and those sort of performances tend to be found in places like aircraft main engine bearings. Thermal speed rating. I just mentioned that we use oil mist to avoid excessive friction heating. Of course, the mere fact of the rolling contact passing stresses the steel, and that causes heating in its own right, and then there will always be some heat generated through the lubricant film. So there's been a lot of work done in recent years, and we now have BS ISO 15312, which gives a thermal speed rating. Bearings generate heat through the cyclic stressing of the steel, through the rolling contacts, and through disturbance of the lubricant. We have BS ISO 15312, which gives a detailed method to estimate the speed at which friction heat generated is balanced by the heat loss rate. Standard steel bearings can be used at temperatures up to 125 degrees C. If they are taken higher than this, it's beyond the tempering temperature, and the body of the steel may start to change. So it's necessary for those circumstances to heat treat at higher tempering temperatures to stabilize the bearing for that sort of operation. In practice, this can be taken up to about 250 degrees C with regular bearing steels, but the hardness will be reduced, and so the load capacity has to be scaled back. There are some special steels available, including, for example, tool steel, which can operate as high as 500 degrees C, but that needs special lubrication, and in practice, permissible operating temperatures are nearly always limited by the lubricant. Radial internal clearance. A rolling bearing needs a correct operating radial internal clearance for optimum life. We make the bearings with an initial internal clearance which allows for the interference on the shaft or the housing, which slightly stretches an inner ring or squeezes an outer ring if it's interference. And this is allowed for so that when the bearing is operating at its normal temperature under its expected load, there will be almost zero clearance. And the correct clearance is almost constant, regardless of the mode of operation. So normal internal clearance is suitable for most situations, but sometimes you need a greater than normal clearance. In these circumstances, it's best to get advice from the bearing manufacturer. An example would be if you have a rotating balance weight, for example, which causes the load to rotate with respect to both the rotating ring and the stationary one, then both rings need to have an interference fit to avoid creep of the inner ring on the shaft or the outer ring in the housing. And in that case, greater than normal clearance is required. Radial preload needs to be avoided at all costs. It will cause rapid and uncontrollable overload failure. The way around this is to use angular contact designs where the contact angle in the bearing is not zero, but anywhere between typically 20 and 40 degrees. And I'll show you in a few minutes how we can use that construction to eliminate play but still manage the deflection behavior without this sort of runaway overload. We also have to deal with coefficient of friction. In rolling bearings, it's not high. The rolling contact itself has quite low friction, as you can see from these values given for mu in the table. And in fact, seal torque and lubricant drag are typically higher than the notional frictional torque of the bearing components themselves. But nonetheless, it is a contributory factor. and these coefficients of friction are important if absolute low rotating frictional torque is essential. So now I want to talk about the basics of how to install bearings correctly, because it's important to avoid accidental loading. So looking at this shaft here, at the left hand side we have the bearing which is providing axial location and taking the live axial load, and of course it will take some radial load. So it has a fixed and loose shoulder on the shaft and two shoulders in the housing, which I've shown by the arrows, and the blue arrows show the axial load direction. The bearing at the other end of the shaft, of course, needs to be axially free. If you use a cylindrical roller bearing, that's dead easy. If you use a ball bearing, then it needs to be located on the shaft, as I've shown on the right, but it must be a transition fit in the housing so that it can slide to compensate for load deflections in the primary bearing at the left, or indeed thermal expansion of the shaft. So just to summarize that, the live axial loads which one bearing is taking must have positive mechanical retention by shoulders. If the ring rotates with respect to load, just to repeat that, it needs an interference fit. If the ring is stationary with respect to load, then a transition or clearance fit may be used, and that might be decided by assembly considerations. The internal clearance needs to be selected, taking account of interference transfer depending on what fits have had to be used, and accidental loads from dimensional tolerances or thermal effects must be prevented by design of the shaft and housing. So here is an example of a rolling bearing life calculation. I've assumed a radial load P of 3 kilonewtons, speed of 1,500 rev per minute, a shaft diameter of 50 millimeters, and a design life requirement of 10,000 hours at 90% reliability. That means we need an L10 of 10,000 times 60 times 1500, which comes to 900 million revolutions. Might sound an awful lot, but it soon accumulates. So from that we can work out a required dynamic capacity by taking the life formula, and that comes out with a capacity required of 29 kilonewtons. So we now need to find a bearing where C is greater or equal to 29 kilonewtons, and if I look in a typical catalogue, a 6210 single row radial ball bearing has a bore diameter of 50 millimeters, an outer diameter of 90, and a width of 20 millimeters. Just to digress for a second, those proportions come from the standard tables in ISO 15. The code for the bearing type, 6 is a single row radial ball bearing, 6.2 is a width series 2, and the 10 multiplied by 5 gives us the bore diameter of 50. Now that has a capacity, radial dynamic capacity of 35.1 kilonewtons and a static capacity of 19.6, a speed limit of 7,000 revolutions per minute with grease, or 8,500 revolutions per minute with oil. So this bearing is suitable for the proposed application. So just to go back to the shaft and housing fits and the radial internal clearance again, it's very important to emphasize this, that if the shaft rotates with respect to radial load, we need an interference fit. And in this case, we're going to use shaft tolerance K5. The load is stationary in this case with respect to the housing, so we can use an installation where we have no axial load on the rolling elements at the location end. We can select a clearance fit, and we can use a housing bore tolerance of H8. The resultant operating radial clearance will be satisfactory because the shaft fit will cause only moderate loss. We're not expecting an external heat source in the shaft, so we can use a normal clearance, which is denoted CN, although this normal clearance these days is often marketed without indication. I mentioned earlier that we can use the angular contact type of ball bearing to manage the free deflection of a bearing. In fact, we can remove it altogether. And the reason we can do this is shown in this diagram, where I've plotted the deflection of an angular contact ball bearing in the axial direction as we increase the load. We start off with a nominally point contact between the ball and its raceways. But of course, as soon as we put load on, because the raceway is a toroid, and the ball, of course, is a sphere, then we have an elliptical patch, and this grows in a particular way. We have initially a very soft spring, and then it gradually becomes stiffer. And because the stiffness occurs after a manageable deflection, in this case about 3 micrometers, we can use this property to manage the deflection properties of the bearing. So here is an example of axial preloading operating. You can see on the blue line is our original bearing, and then an identical bearing opposing it, facing the other way if you like. And we have deliberately machined away the faces between the bearings so that they are mutually deflected, and we now have a preload point. There is no free play, either axial or radial, in this assembly. So we have avoided radial preload, we are using axial preload, and because it's axial preload, the rolling elements are somewhere between 20 and 40 degrees, and if a radial load appears, they can deflect axially as well as radially. And of course, if we continue to apply load, as I've shown with the big blue arrow, the bearing on the right will gradually shed its preload, and then we shall be on the straight, stiffer deflection curve of the left-hand bearing all by itself. So this is a very useful property, and the next slide shows an example of this. This is a typical advanced duplex double row hub bearing for a motor vehicle, and you can see how I've illustrated the load paths from the contact angles of the balls, and it's like a man stood with his leg apart. It makes a very rigid assembly. There's no free play in this bearing, so it provides very precise tyre tracking, and this is preloaded at the factory. So the motor manufacturer simply has to bolt on the finished assembly. It's all managed inside the bearing factory, and it has very robust sealed arrangements, and this should be typically good for 150,000 miles unless something goes badly wrong. So here's a little bit more detail on the axial stiffness of the preloaded pair. You can see the preload-unload point now, which I mentioned earlier. You might not have grasped this initially, so here's another slide just to show it again. The red line is the increased axial stiffness of the preloaded pair, and then when we get to the preload-unload point, we're on the by now stiff curve of the bearing which is carrying the axial load, the live axial load. So I hope that helps understanding. I have here a short bibliography. First, I need to refer to the Tribological Design Guide Part 1 Bearings, which is published by IMechE and continues to be available. And that was prepared by several of my colleagues in the Tribology Group and derived from an initial edition that was published in October 1995. And some further sources can be found in the Tribology Handbook by the late Michael Neal. And then I've listed some data sources from the Engineering Sciences Data Unit, ESDU for short, and also referred to the catalogues of some of the major manufacturers of rolling bearings who will always be prepared to help you with a bearing application. And that's at the end of the webinar. I hope you found it interesting. Thank you.